So in this section, we're going to define something called a vector space. We're going to build up to that, though, over a few pages of discussion, starting with a discussion of a seemingly innocent little theorem about linear combinations of vectors in Rn. And here it is. The theorem says that a linear combination of linear combinations of vectors in Rn is a linear combination of those same vectors in Rn. So there's a lot of words going on there, so let's parse this. Here are our vectors in Rn. And here you see we have some linear combinations of those vectors in Rn. And the theorem says that if I were to take a linear combination of those linear combinations, if I were to take a linear combination of those linear combinations, that this result would be a linear combination of the original collection of vectors. So let's see if that's true. Now, we see what we have here. We have our linear combination. We have our linear combination of our linear combinations of our original vectors in Rn. And let's multiply it out and see what that actually turns into. Okay. Well, this is just algebra at this point. You take these formulas for these L's, stick them in there, like so. And then take all of this, multiply it out, collect terms, which gives you this. And notice that what we have is, in fact, a linear combination of our original vectors in Rn as required. And you see right here what we were supposed to show is that this ends up being a linear combination of those vectors in Rn. Okay, so done. Gosh, there's a certain amount of algebra that goes into that, and parsing, etc. But we were able to prove this nice result. And by the way, we will be using this result here and there. It comes up surprisingly often, but a linear combination of linear combinations is a linear combination. Fine. So now, suppose that at some later date we find ourselves interested in taking linear combinations of functions. Well, you can imagine how one would talk about linear combinations of functions. You can take functions and multiply by scalars. You can take those results and add, and so linear combination makes sense for functions. And you might consider, hey, I wonder if it's still true that a linear combination of linear combinations of functions is a linear combination of the original set of functions. Well, the ideas would have seemed to all be in this proof, right? The only thing is, we can't just cite this theorem, because this theorem, as stated, is about vectors in Rn, and functions are not vectors in Rn. Functions are a different kind of object. So, unfortunately, finding ourselves interested in linear combinations of functions, we have to state and prove separately a whole new theorem. And here it is. A linear combination of linear combinations of functions is a linear combination of functions. Totally new theorem. We have to prove it all over again effectively as well. Here's the functions that we're starting with. Here are some linear combinations of those functions. I can consider now a linear combination of those linear combinations of our original functions. And I can then take that and take this, substitute it for what that is, take that, substitute it for what it is, take this resulting expression, multiply it all out, collect terms. We get this result, and note that as required, it is indeed a linear combination of our original functions as required. It is a linear combination of our original functions. Okay, well, gosh, that seemed really familiar. This proof here seems to be practically exactly the same thing. Certainly the ideas are all the same as this proof that we did at the start. It feels like we're reproducing work. Okay. Oh, well, so be it. But now we at least have a theorem that addresses our interest in linear combinations of functions. Okay. Now suppose we find ourselves interested in linear combinations of other kinds of things. Well, gosh, are we going to have to do this all over again? Are we going to have to restate effectively and reprove seemingly this exact same theorem every time we find ourselves interested in taking linear combinations of different kinds of things? This is going to get tedious, right? This is something that we want to avoid, this kind of tedium. So there's a wonderful way to address this this situation. The way we address it is with something called an abstraction. We're going to see several abstractions in this course. This is the first one. The whole idea of an abstraction is we list properties that are satisfied by our objects, but we very importantly never say what those objects are. So we're going to talk about what you can do with these objects, but we're never going to say what the objects are. These properties that they satisfy, we're going to be careful to indicate properties that we need specifically for what we're doing. Again, though, we're never going to say what the objects actually are that we're talking about. Having done this, having defined an abstraction by certain properties having been satisfied, we're going to state and prove our theorem about the abstraction in the abstract, never having specified what the objects are that we're talking about, leaving that open for whatever it might be in the future. Simply using the properties that we've specified. Then we have a theorem in the abstract, and what's wonderful about this is that any time you find some specific example, as long as you check that your example satisfies the required properties, then the theorem automatically applies to your specific example. Okay, it's a very powerful idea. We'll see an example of this momentarily, in the next lecture. Looking back to the theorem that we were looking at here, and I'll look back to the first example. This first example, you see we're taking linear combinations. That means that these objects, whatever it is that these objects are, be they vectors in Rn or be they functions, whatever they might happen to be, I'm going to need to be able to add these objects, whatever they are. I'm going to need to be able to take these objects and multiply by real scalars. And I'm going to need to be able to do what I'll loosely call standard algebra. I'm going to need a distributivity property and an associativity property, and things of that sort, standard algebra. So that's what we're going to specify here. For those previous theorems, what we need is to be able to add whatever these objects are. We're going to need to be able to multiply them by scalars, and we're going to need to be able to do standard algebra. These are about to motivate for us in the very next lecture an abstract construction that will allow us to prove a large number of theorems all at the same time.